but I know Adam likes to push the time limit, so I'm going to get a head start on my introduction and keep it fairly short. Welcome to the 5th talk in our seminar series on gravitational wave astrophysics. We've been having a great time so far, but today we're going to have a real big blast and boom. I'm truly honored and delighted to be able to have invited Professor Adam Burrows from Princeton today. Adam's research interests have been broad and very wide-reaching, and I can list here a couple of them, including supernovae, which is a discussion today, exoplanets and brown dwarfs, planetary atmospheres, computational astrophysics, and nuclear astrophysics. And these aren't just kind of surface touching on these, but these are real pioneering efforts in these fields, and writing many fundamental and influential papers and reviews over the last 30 years.
No, please, thanks.
I got to ham it up for you, don't worry.
That was the 30 years.
I was reminded that Adam is familiar with the area as he got his PhD from MIT before having got his undergrad degree at Princeton, which he is at now. I also won't hide from the fact that my own original motivation for suggesting gravitational wave astrophysics as a seminar series was based on today's topic on supernovae. And I know I'm biased, but I'll say I think that this is truly one of the most exciting aspects of the field because we're charting the unknown. Black hole mergers are old news in the sense that we know what they're supposed to look like, and to some degree you can say you're just trying to measure rates. There's a known unknown. But here, with supernovae, this is uncharted frontier. We don't really know what we're looking for, although we have some hints, and I think Adam's going to discuss this. And thankfully, supernovae are very loud, at least observationally, across the EM spectrum and produce copious neutrinos, in addition, we hope, to gravitational waves. So without further ado, Adam, please.
Thank you, Dave. I always enjoy visiting Harvard. There are lots of colleagues that I've known for many, many years, and I have opportunities to discuss things with them. I apologize that I'm going to be here for such a short time. But during this time and during this talk, I hope to communicate to you some of what I think are the most important bits of progress in this subject. This is the perennially unsolved problem. Core collapse supernova theory has been with us for 50 years. The original ideas, the original good ideas, involved neutrinos, and in fact, that survives. But what I hope to communicate to you today is that we're very close to a solution to the problem. And I, in fact, haven't been as optimistic in the last 20 years. And so, without further ado, let me first introduce my collaborators. This work, of course, is sometimes very complicated. There's a lot of computational effort involved, although I hope to convince you that there's physics. And the physics aspects, some of which have been ignored in the past to too great a degree, may be looming large. But my colleagues, Josh Dolans and Aaron Skinner, David D'Artagnan, David Radice, and Victoria Morozova have been central to this work, and I want them to get sufficient credit. This is just a summary, very quick. People, I'm sure, are familiar with the backdrop. You have a massive star, its core achieves the Chandrasekhar mass. It becomes unstable and collapses. It collapses within about a half a second. The central object is about the size of the Earth. It bounces because it achieves nuclear densities, and you get a spherical piston. But that spherical piston drives a shock wave that stalls. And the supernova, an explosion, is a shock wave that moves out. And so we've been spending a lot of time trying to revive that shock. Now, the direct mechanism is that shock wave just unimpeded going out through the envelope, but that never works. There are 1D mechanisms, though, that involve the neutrinos, and I'm going to show you that we can actually get explosions in spherical symmetry, but only for a small subset, and I think this is emerging from the community, actually, to inform our understanding. We actually get 1D explosions. But the major crucial problem has been that these things are convectively unstable and turbulent. And the turbulence seems to be central to the mechanism for most of them. The turbulence actually involves a significant amount of turbulent pressure. And pressure is part of the game. If you can get a lot of pressure behind the shock, you can revitalize it. In fact, you can almost make it not stall. And so we've had to do multidimensional turbulence, radiation hydrodynamics or magnetohydrodynamics. And that has been inaccessible until fairly recently. And even some of the approximations that we used in the past, we still have to use. So 2D and 3D convective simulations seem to be necessary. You also perhaps have a very rapid rotation in some contexts, but I think that's a subdominant class, and that may give you hypernovae, and I'm not going to talk about that today. But the convection and turbulence in the multi-D context, still with the neutrino driving, seems to be actually obtaining. Well, what are the important ingredients? For years, we've been inheriting progenitor models that have been evolved with high art, but in spherical symmetry, of these massive stars. And those profiles that we inherit, the density profiles and the rotational profiles, may not be credible. There's been a lot of good work on that, but there's going to be a new generation of simulations that are actually multidimensional stellar evolution calculations after core oxygen burning, after oxygen burning starts. And so we can get the turbulence structure, we can get the redistribution of angular momentum, we can get perhaps some better ideas of the magnetic fields, although I think they're not as important. But I hope to emphasize, I am emphasizing to you that in fact, the progenitor models are crucial. Once you have the progenitor models, everything else follows. So that's one of the keys. As I mentioned, multidimensional radiation hydrodynamics. I'm going to show you merely 2D simulations because we can do 2D, we can do a full 2D radiation hydro simulation in 2 days now. That's a big jump, so that we can actually afford to make lots of mistakes. We can't afford to make lots of mistakes in 3D. So we've done a lot of tests. We've done about 50 2D models. For comparison, about 20 years ago, you published one at a time. So there's been progress in that. The neutrino matter interaction processes people thought had converged. It's MEV physics. You have neutrinos interacting with matter. It's laboratory stuff. It's been known some of it's been known since the 50s, and it's basically been known since the 70s. It's a particle physics problem. However, there are many body effects. The same sorts of things you worry about if you go to a synchrotron light source. You're hitting a crystal or a liquid. There are correlations between the individual molecules or atoms. Those correlations affect the interaction between the radiation, whether that's X-rays or neutrons or neutrinos, and the matter. And at low densities in this context, low being 10 to the 8 grams per cubic centimeter, 10 to the 9, etc., it's not a big effect, but we go up to beyond nuclear densities. And in those contexts, the many-body effects can be factors of 2 and 3. Now, what I'm going to emphasize is even factors of 30% make a difference. And recently, there have been calculations that indicate that our cross-sections could have been off by 10 to 30%. Now, that may seem small, but it's all systematic in a certain direction. Now, general relativity is important too. We've done a lot of simulations with Newtonian, but we have to do at least approximate general relativity these days. And I'll show you those results as well. Okay. So what are the important ingredients in doing these types of simulations? The important ingredients involve, the physics involves the neutrino matter interaction, and in particular the inelastic processes, neutrino electron scattering, because it's a redistribution process. Neutrino nucleon scattering, and these many-body corrections. I'm not going to go into great detail in the physics. I can do that in questions, I can do that offline, etc. But I'm going to show you some of the consequences and try to convince you that it actually is important. General relativity, but also the initial perturbation seeds. You have turbulence, you need perturbations. You need seeds for the turbulence. If it's perfectly smooth, which nature can't really be, then you don't get these instabilities. You get the instabilities, but you don't get the manifest, and they don't go nonlinear, etc. So you don't get the full turbulence. It's also the case, and this is going to survive when we really understand everything, that the results are stochastic. Because of the turbulence, because of the chaos in the flow, little changes will make a difference. And so the energy of the explosion of a 15 solar mass star is going to have a distribution function. Okay. There's also the issues of resolution and numerics. This is a real pain. And it forces you to partner with applied mathematicians, which is also what I said. Are you taping this? They have their virtues, though, as we all do. Okay, I want to talk about some of the other groups because they've been doing some nice work as well. The Oak Ridge team this is the shock radius in kilometers, 250 kilometers, 0 kilometers, etc., versus time after that bounce at nuclear densities. And when they do the calculations in one dimension, they get that red curve. That's just spherical symmetry. But when you turn on the convection, and again, this is 2D with axisymmetry, you get all sorts of, when you turn on the 2D, you get all sorts of instabilities. They have to have seeds in there, and they get these explosions. And these are for 1D, 2D, and 3D, etc. There are differences, and I can talk to that a little bit later, although that's not the emphasis. But the important thing is that the shocks are revived. This is another group, the Garking group, the Max Planck group, and they do the same sorts of things. These are the same sorts of plots, and these are for different progenitor models, an 11.2 solar mass, a 14.4, etc., going up in mass. And they all explode, but they explode at different times. The time of explosion is important in the energy and all the systematics, and it'll also be important in the signal in gravitational waves and neutrinos.
Hey, Adam, when you have a mass like that, is that a zero-age main sequence?
Yes, good point. Yes. And some of these models, in fact, all of the models have some prescription for mass loss. It makes a difference at the margins. Yeah.
The big discussion about the binary companion making a big difference for LIGO sources. Do you expect that to make a big difference?
It's hard to tell. It depends on when the mass transfer happens. If it's a case A, case B, it makes a difference. If you do the mass transfer after, for example, at later times when after core helium burning is ignited, it doesn't make much difference. It can make a difference in the rotation, in the rotational profiles in the interior, because the gravity can reach to the interior, and you can get these torques. And so if the rotational structure is important, and the binaries are fairly tight, and there's binary evolution, such as you alluded to, then it can make a difference in that sector. I'm going to argue that rotation is a subdominant contribution to the whole scenario. But you see that the explosions in these are different times. I don't really emphasize this. This is actually for one model, but this group actually gets the explosions at almost the same time. So that's a difference in the models. And what we'd like to know is why. And the bottom line is, it seems as though we're all doing about the same calculation, but when you're near the critical point for explosion, little things make a difference, and I hate that. I had argued for many years that the big picture will emerge, and the rest will be details. Well, when you're near the critical case, when you're almost explosive, then changing things a little bit in the neutrino sector, hence my 10 to 30% that I alluded to before, can make a big difference, and I'm going to demonstrate that. So there are these differences. This is a summary of those two group simulations. Here's the Oak Ridge simulations for the same models, the explosion almost immediately, and here are the dash curves here are the Max Planck simulations for the same models. This is 0.2 seconds, 0.6, and that's a long time in this game, right? Okay, so what could be the reasons for these differences? Some models that we did recently are right here, but those aren't our final models. Okay, a lot of details. Why are we witnessing all these differences? Unfortunately, there are some details, but what I'm going to say is the details are starting to converge among the groups and perhaps with the physics, and we're all getting explosions. We are now, our group, are getting explosions for every model. This is new. Okay, so I've already said a lot of this, so I'm not going to dwell on this, but there used to be Mazurek's law, which is sort of informed by the 1D simulations. It summarized, no matter what you do, it doesn't make any difference. And I had been articulating this for far too long, and I might have been wrong. When you're close in multi-D putting you close, then it does make a difference. So in meeting many-body structure factor corrections, which we knew about a number of years ago, but thought were important only at high densities, seem to be modestly important at low densities. And it's all going in the right direction. And then the differences between the groups, spatial and energy resolution, but there's also this thing here. We don't do transport the same way. Because this is so expensive, A number of groups, we don't do this, but a number of groups have actually done, in multi-D, they've done multiple 1D simulations, which they call ray by ray, which if you know anything about specific intensity is very misleading, because these aren't specific intensity rays. They do a 1D simulation along a particular radius, and then they map that, they couple it to that region in the 3D or 2D simulation. Then they do it over here. Do it over here. That is not real transport, because at any point you get radiation from many different angles, and they ignore that. And so we've written a paper, published a paper, after they accepted the paper, it's out, showing that with our code, which we can actually compare for the first time, because the way they had set it up, they couldn't do both the real transport and the ray by ray. We showed that the ray by ray systematically makes it more explosive. Now you'd like that maybe, but that's part of the emerging insight. The initial progenitors, the seeds, etc. The equation of state makes a moderate difference. There are these technical things. Okay. Now, this is just a very quick set of simulations comparing the outputs for a given model with the same ostensible physics for different groups.
Adam,
Yeah.
you said you do real radiator transfer.
Oh, no.
Are you going to talk about that, or can you say in 2 sentences?
I do almost real radiator transfer.
Okay.
We can't do full multi-angle transport in 3D.
You're doing a moment approach?
We're doing it's 2-moment closures with velocity dependence, with approximate general relativity. So it has the redshifts in there.
Like M1.
It's like M1, exactly, like M1, but it's still multi-D. And we're doing a study of the closure dependencies, yes.
Oscillations are not important.
Neutrino oscillations are not important for the mechanism, but they are important for the detection. Because you do get oscillations, MSW, in the envelopes. And that's an interesting tale. I'm not going to go into detail there, but I will mention a few things. But at the high electron densities inside most of these cores, the MSW is completely irrelevant because the delta M squared is the wrong regime, but you also don't get these spectral swaps and spectral splitting. You don't get the effects of neutrino on neutrino oscillations because you have electron density giving you the background lepton effect. And so it completely swamps the effect. You could get this in merging neutron stars. Merging neutron stars, you have a lot of vacua. You have vacua around pretty quickly. So the neutrino densities, the lepton densities from the neutrinos could be very large compared to the electron densities. And so the oscillation effects in the early stages of the emerging neutron stars, to the degree that neutrinos are important, driving winds, nucleosynthesis is important. Now, I hope to convince you that these curves look pretty similar. These are completely different codes, ostensibly using the same physics, but of course they have different resolution, they have different approaches, but we get this is the neutrino luminosities for the electron types and anti-electron types. All I wanted to show is they're almost the same. So why are there such differences? Okay, I keep saying that. So we introduced this new code. It's not perfect, but it's pretty good. And one of the advantages of the code is the following, and that's why we can do a simulation fairly quickly. In the past, people did simulations using implicit radiation hydro. Implicit meaning you had to do iterations to get the solution any place over the entire space, everywhere. So you had to converge a big matrix. That was thought to be required, but in the core collapse context, the speed of sound and the speed of light aren't that far away after bounce. We're already limited by the speed of sound, the Courant condition. So we might as well put the speed of light equal to the speed of light and do the calculation explicitly, because we're limited by the light travel time across the zone. It's not much different from the sound travel time. So we're still stuck with microsecond time steps. I hate to say that. So 1 million time steps, for example, for a decent simulation. But we can do the calculation without doing that iteration. No Krylov subspace methods. You do local calculation, so it's all explicit. And that has sped up our calculations by a factor of 5 to 10. Okay. So we can make mistakes really fast. Okay, say there's a lot of detail here, so I don't want to go through it. And it scales pretty well. We're redoing the scaling because we have to, unfortunately, go to Knight's Landing architecture, which requires threading, and this is for the cognoscenti. and an OpenMP hybrid model, in fact, MPI OpenMP hybrid model of the parallelization, and that's challenging. We're just getting that going right. All right, a lot of advantages. Okay. So what I want to do is to show the sensitivity to changing various things in this space. This is, again, the shock radius versus time, and you see that's explosion. And we change various things. We include various physics, like the medium correction, that many-body correction, inelastic scattering of electrons, or no, inelastic scattering of nucleons. You'd think that inelasticity, do people know what I'm talking about? If you scatter off a nucleon, a neutrino of 10 MeV energy or 20 MeV energy, hitting a 1,000 MeV mass neutron or proton, you don't think there's much recoil. And there isn't a lot, but there is some. And so you're doing energy transfer to the nucleons by scattering. And it turns out, because the cross-sections for that process are pretty large, the small energy transfer times the large cross-section makes an interesting energy transfer and changes some of the dynamics. You also have the electron, the neutrino electron scattering. It's just like Compton scattering, just different cross-sections. And so the electron is really low mass, and the energy transfer is huge. It's Compton scattered. But the cross-section is really low. So low cross-section, big energy transfer, high cross-section, low energy transfer, they're comparable. So we have to include them. And that's actually the most computationally intensive aspect of this, because we have to do energy redistribution. However, you can see when we change a few things here and there, we get explosions at late times or at early times, depending. We can also get explosions if it's Newtonian, which is a new thing. People thought that the GR was really important, if you have these changes to the cross-sections. And so this is just a summary of some of the results. So we get explosions for almost everything. Some of the explosions take a long time. But when we put in all the physics, we get explosions pretty robustly now. But when we get explosions, and the energies of the explosions depend on some of the details. If we had a very weak late-time explosion, and then we put in perturbations by hand from the initial turbulence of the thing that collapsed, a fairly large number, in fact, we can get a shift in the time of explosion in some of the details. We use that ray-by-ray approach, that multiple 1D calculational approach. Instead of exploding here, it explodes here. That's a big difference. And some of the differences go like this. And this is what everybody else in the world has been doing until recently. There's some nice work that's emerging from Sean Couch and Evan O'Connor that isn't using this. We've all started to try to do the right thing. This many-body approach, though, can make a huge difference. And all it does is it decreases the neutrino-nucleon scattering cross-section. And it's not so, the most important neutrinos are the electron types and the anti-electron types. But there's all the other four species too, sort of lumped together as mu types. The electron types aren't changed that much in this many-body correction, because the scattering isn't that as important as the absorption. For the mu-type neutrinos, which people have generally ignored as being important, this is an important aspect. This scattering off nucleons is the dominant process. And so if you change that by 30%, you change the emissions in that neutrino channel by something like that. And what does that do? What that does is the cores collapse, and when you lose more energy, it shrinks faster. That doesn't sound good at all. But when it shrinks faster, it compresses the material. That material gets hotter, and it heats the electron types and the anti-electron types. So what emerges is a harder spectrum. And it's those that drive the explosion. So losing energy in that sector, making it more compact, actually energizes the neutrino matter coupling, because it's the electron neutrino coupling to the nucleons behind the shock that drives the explosion. So by indirection, this decrease in the cross-section, which increases the losses, actually enables the supernova. And that seems like a secondary thing, and that's why people didn't notice this. Some people sort of do really fancy transport and then put a sort of leakage scheme in for the muse because they didn't care. Turns out to be crucial. So we suggest. Okay, and so this is with and without that structure factor effect. Structure factor on the right and the otherwise on the left. Only 2D. And you see the heating behind the shock is much more vigorous. These are, again, axisymmetry. And it explodes much earlier. Otherwise, everything else is the same. Even the resolution. Even the computer. I think in 2D, though, the real problems with 2D are the morphology of the blast. In 2D, you have this axisymmetry, and you see that you have these funnels and plumes coming in. Those are actually rings. Nature's not going to do that. It's going to break up. And therein hangs a tale, because we see that the explosion energies are directly correlated with the anisotropy of the explosion. If it's very anisotropic, you get some fallback on one side, and you waste a whole hemisphere of neutrino energy deposition. If, on the other hand, you have more spherical explosion, we get energies, our highest now is 2 times 10 to the 51 ergs. That's the highest anybody's ever gotten, except in MHD. Yeah.
Look at the central region fixed.
No, it just looks like it.
Okay, you actually solve, you don't fix it.
No, it doesn't. That's the other thing. This code doesn't do that. Everybody else's simulations, they do the inner region in 1D, even the 3D simulations. And one of the things that took us time to get this code going was that we didn't want to do that because we wanted to have recoil and kicks and these sorts of things. And the way we got around this was we use a so-called dendritic grid. We use a spherical grid, but as you go in, you have the converging zones, and in the angular direction, you have this Courant hit. And so what we do is we de-resolve like adaptive mesh refinement. But it's static mesh refinement. We statically resolve the inner region by this de-resolution. The zones stay the same size, but in the center, we don't have the angular hit in the Courant. So it's like doing AMR, but we don't have the A. Yeah?
Quick question. So all these simulations seem to show a scale which is a few thousand kilometers per, few thousand kilometers. But the star itself is
Yeah.
almost magnitude.
Yeah. That's always a problem. We go out to 20,000 kilometers. And
So what do we mean by explosion here?
good point. These are ostensibly exploding on the grid, get out to about 20,000 kilometers per second, and the total energy of the explosion is in excess of the binding energy of the entire star. So we include the binding energy of the outer regions, and I'll mention that. That is crucially important to what objects explode. And since you brought this up, the binding energies generally increase in the exterior with progenitor mass. There's a variation. And you can get huge binding energies. You have to get at least 2 times 10 to the 51 ergs at a minimum in order to get zero energy at infinity for some of these. That means you have to have 3 times 10 to the 51 or something like that. I don't think you can get it. And I think that's going to go to a black hole. So there's a barrier to overcome. All right. I already showed this. Again, I want to emphasize this basic point, that you can change the physics just a little bit. These are 10 to 30% effects at densities below 10 to the 13 grams per cubic centimeter. But you can change when it explodes and how vigorously it explodes by quite a bit. And all we're doing is exploring the changes in the physics. We haven't been able to do this, and nobody's really done this except for inelastic scattering and spherical symmetry and a few other things. Have actually compared calculations with and without things. That may seem peculiar, but that's almost completely true.
So, Adam, this time of explosion,
Yeah.
is that kind of directly correlated with also the energy of explosion?
It's not as directly correlated as I would have liked, but it's weakly correlated.
In which way?
Earlier the
Early
better.
guys
Earlier,
are
yeah, because you're wasting all the neutrino energy deposition all the way here, because no matter how much energy you deposit, it doesn't accumulate. You're re-radiating it. The matter is flowing through the shock. It's an accretion shock. So you heat this matter, if it doesn't explode, that matter is going to be buried in the core, and you've lost. You have to do it again, and again, and again. It's only when you kick the explosion that the neutrino energy deposition drives subsequent motion. You're heating the material. Okay. again, example of a ray-by-ray difference. You do with and without this ray-by-ray approach. And so I think that's introduced artifacts into the literature we have to overcome. This is just a summary of something. For our benchmark models are the solid curves. These are for 12, 15, 20, and 25 from Woosley and Hager 2007, or Suckbold 2015. And we get pretty robust explosions. And by the way, I used the word robust once 20 years ago. I got so chided that I haven't used it since. So you're the beneficiaries of my evolution.
Now it's really robust.
And if we didn't have some of these effects in there, we get explosions here. And in fact, the 12 and the 15 don't explode. So there are things that are necessary. You have to put in all the physics, but even the many-body effect seems to be crucial for some of these. So there's a huge range of possibilities if you don't do this. And I will say again that each one of these is a small contribution to the overall energetics. But they generally go all in the same direction. Yeah.
Briefly, going back to when
Briefly.
they weren't exploding 10, 15 years ago, were these elements missing from there? Has the process, what's the dominant changes between those? What do you say?
It's basically, I said that relativity wasn't important, but if you don't include the many-body effects, people didn't get explosions until they got relativity in there. Because relativity does the same thing as the mu neutrino losses. It makes it more compact. You get a harder spectrum coming out, and the neutrino cross-sections go up with the energy. So you're more strongly coupled. It's bringing all these things together and then being able to make mistakes quickly. You didn't want to make any mistakes. 2D used to be the state of the art.
So it really was the multiple elements of the physics.
They're all going in the same direction. So the many-body effect's important, the general relativity important.
And how do you know that you are done? Because in
Yeah, that's right. That's right.
once you have
That's right.
explosions, you declare victory, but then
Yeah, no, and we've done that before. So that's a very, it's a very good point. What we need to be able to do is not only to get explosions, but we need to be able to explain, at least qualitatively, the energetics of the explosions, the magnitudes of the kicks. We need to be able to connect with the data. We're almost credibly starting to do that. I don't think we're credibly starting to do it yet. But we now have a range of energies that are represented by nature. Previously, when people declared explosions, for example, the Max Planck group doesn't have any high energy explosions. They're all a few times 10 to the 50 ergs, no matter what. The Oak Ridge team, they get energetic explosions up to about half a beta, 10 to the 50, 0.25 times 10 to the 51 ergs, and getting higher than that. You have to include the binding energy of the outer envelope. As I say, our explosions depend on how they explode, and I think that's where 3D is going to be crucial, because 3D is going to explode the same way 2D does. It might explode at the same time, and with the same basic physics in there. So we have our work cut out for us. Okay. Just to show movies with and without putting in extra seeds. These are just perturbations. You can see if you seed it early on, you get early vigor. If you don't seed it at all, you have numerical noise as the seed. You want to control that. And these oscillations are basically the oscillations due to neutrino-driven convection, and subdominant is the so-called SASI, is the standing accretion shock instability. But the convection is the most important. And you see the type of explosion you get here. And the morphologies vary all over the map. And that's stochastic. That's chaotic. The same model will explode in different ways if you just put in different perturbations. But I just wanted to show the types of differences. This is quicker, etc. And that's the type of difference for some of the models. Okay. So I wanted to emphasize the following. There is abroad in the land, in the world, the idea that the compactness parameter, which is a measure of how dense the envelope is at a certain radius, is a one-parameter family predicting what is going to happen. It's directly connected with the density profile. That is important. But that profile is a multidimensional thing, many different positions and radius, and you also have rotation, which hasn't been factored in well. But when people calculate this compactness parameter, they get a plot like this versus ZAM's mass. 20 solar masses, 30, 40, 50, 10. Most of the mass function is down here. And they say that the low compactness parameter gives you explosion. And what we found is that's just not true. When you have a low compactness parameter, it could be, and this is just that measure of whether there's a tenuous envelope or whether it's a dense envelope. But it's a very crude measure, one-dimensional, one number. When we do the calculations for the lower mass end here, for the 12s and the 15s, for example, we don't get explosions without more help, like the many-body effects. So the old calculations didn't even explode when we got rid of the ray-by-ray, which helped things to explode. When the other groups get rid of that, they're going to have more problems exploding unless they include the new physics. So, but that has they can have low compactness parameters, so that should have been easy. Conversely, up here, the compactness parameter is getting large, and this is really ramping up. This is about a little bit less than 25 solar masses. But let's say the 20 solar mass. Our most energetic explosion is right here, much higher than this. And the reasons were obvious. And we had actually said this. When you stall, if the shock stalls, you still have a large accretion rate. The amount of mass behind the shock that is absorbing those neutrinos is larger if you have more dense material falling in. You may not have exploded, but now you have a lot of material that absorbs the neutrinos. And the power that's being deposited is the optical depth times the luminosity. L tau. Very simple. If you have more tau, you have more L tau. The problem has been that what the explosion is a critical condition. It's actually a dual catastrophe, if you like, where you have control parameters, which you can write down as the luminosity coming out, which is involved with heating, and the accretion rate, which is involved with the accretion tamp. It's holding it in. And those two things are fighting. The fact of the matter is they're connected. The larger the accretion, the larger the luminosity, because you have accretion luminosity. But you can break it up into these two parameters. And because of that, people said, well, if you have a lot of m dot, that makes it hard to explode. But they were forgetting the other side of the equation. And so it turns out the other side is more important. Once you get explosions, you now have a huge amount of mass there, a large tau, and so you have a large power deposition just when you need it, inaugurating the explosion, getting it going. And that you get with massive stars and not with low mass stars. The low mass stars have tenuous envelopes, and so the tau is small. And even once they start to explode, the amount of energy deposition to drive the explosion isn't as large as for the larger mass ones. However, there is a caveat. The binding energy of the outer material that isn't involved in the explosion also goes up with ZAM's mass. And I've superposed with these dots here, the red dots, the binding energy is exterior to 1.5 solar masses. That's an arbitrary number. So you might want to leave behind a neutron star, for example. This is baryonic. And you see they go together. So compactness may not be important for the reasons people thought, but the binding energy aspect of compactness is. These numbers are pretty small. This is 0.1. Oh, this binding energy over here. These numbers are pretty small. This is out to 15 solar masses. You get to about half a beta. We can overcome that pretty easily. And at lower masses, lower values. But over here, look at that. 1.5 times 10 to the 51 ergs is the penalty you have to pay before you can play. So that's starting to become difficult. It's this obstacle that will determine what goes to a black hole. And it gets worse as you go up in mass. So on the one hand, the amount of energy that you'll get in the explosion goes up with mass, but the penalty goes up. And the question is, which wins? And eventually, there's a limit to how much you can actually get energy deposition, and there isn't really a limit to how much the obstacle can be. And so the obstacle is going to win. How this works out is not clear. But it seems as though there's going to be a peak in the energy of the explosion of a supernova. And that the energies of the lower mass end are going to be the lowest. It may not be monotonic, though. We had trouble with the 12 and the 15. We didn't have so much trouble with the 16, the 17, the 20. And we have a lot of trouble with the 30 or the 25, and we're doing a 60. There are a number of things that we're doing here. So exactly whether it's monotonic is an open question. But there does seem to be a mapping, approximate mapping. So that's one of our major conclusions. Here are the binding energy curves. If you just cut along here, this is 2 solar masses interior. And this is just a progenitor model. If you cut right there and you had you want to leave behind half a solar mass, you'd have to pay this penalty. And this is for a 15 solar mass star. That's not going to happen. You want to bury your binding energy problems. And that's what a neutron star does for you. It's 1.5 solar masses. You go out to 1.5 solar masses, you have to pay that penalty, that penalty, that penalty, that penalty. It gets worse. So there's the 40 solar mass, and there's the penalty you have to pay if you want to leave behind a neutron star. Even a 2 solar mass neutron star, which we know exists but probably are fattened by accretion, subsequent accretion. Okay, so that's an important issue. Okay. Yeah. All right, so that's just a summary of some of the things that we've had to study in a little bit more detail to see what the real physical effects are. And relativity helps, even though it gives you more binding. You know, general relativity is deeper potential wells. Pressure is a source. That would seem to be negative, but you can bury that problem in the outer envelope at 100 kilometers instead of 10 kilometers of neutron stars. It's not as bad a problem. Seed perturbations are important. These inelasticities, which are computationally intensive, are more important than I would have expected. They don't seem to be crucial, but one of the things that's new is these many-body corrections. Now, I haven't talked about the physics of the many-body corrections. And I'm not going to. But I will mention one thing. This is what gives you Brouillon scattering. I always pronounce that wrong, but the scattering off crystals. When you're doing DNA studies in the 50s, you're going to get all sorts of interesting diffraction patterns. Those patterns are because of correlations in the positions of the things off which you're scattering, because the wavelength of the probe is larger than the interparticle spacing. And so you excite these things simultaneously, and amplitudes add, and then you square for quantum mechanics. If they're far apart, it cancels out. The sky is blue because of scattering off the atmosphere, it's Rayleigh scattering. The wavelength of the radiation is larger, let's say red light, is larger than the interparticle spacing of the atmosphere. And so there's going to be correlated effects. But there's no interaction between the molecules. And so when you square the amplitudes and you average over that region, that average is Poissonian and the square goes linear. Average n squared goes as n. And that makes it seem as though you're scattering off individual molecules. But when there's a correlation, when you have interactions between the molecules, the atoms or whatever is scattering, those interactions will cause correlations in the positions or the spins of the species. And those correlations will affect the final state scattering rates. And at low densities, the nuclear effects aren't so large, but as you get up to higher densities, there's a nuclear interaction. And you have to include that in the interaction between radiation and matter. And that effect is what I'm talking about. Okay. I'm going to as quickly as I can, go through this. And this is a nice bit of work we submitted that was led by David Radice at Princeton. So what's happening for the lowest mass progenitors? There's a whole lore to this. And here's the density profiles. These can be really steep. Look at that. You go, this is the binding energy. Density profiles. Really steep. And so there's almost nothing out there. The compactness is really low. And then you just go up in mass, and we do 8.8, 8.1, 9, etc., up to 11. Those are the low mass range. And here's the density profiles. And we can do all these calculations in 1D, etc. And some of these actually explode. This is a 9.6 model, solar mass model. It's zero metallicity. But the evolution gave a really steep density drop-off. And this is a 1D simulation where this is just, these are mass shells. They're falling in, hit by the shock, and ejected. And there's the vacuum that is emerging around the neutron star, which is there. And this is, I can't tell you how excited I was about this particular plot, because I was always hoping that we'd be able to solve the problem in 1D. and these plots would be useful. You can't do these types of plots in multi-D because you don't have mass shells, right? It's not spherical. So I can't use that as a Lagrangian coordinate. Anyway, maybe I just get excited by simple things. But here, you get explosions. This is velocity profiles. That's a positive velocity. We get shock speeds that are 20,000, 10,000 kilometers a second, robustly. This is a 1D model. Other groups are getting this too. There's nice work done at the Max Planck group, and they're getting these types of explosions too. So in the 9.6 explodes, the 8.8 explodes, the 8.1 explodes in 1D. Those density profiles are low. But the 9 doesn't. They're not monotonic. In 1D, you don't get explosions. There are people that said that everything up to 10 solar masses is so-called oxygen, neon, magnesium core collapse. Many of those do not explode in 1D, despite what you might see in the literature. They do not. Just, we've done it. Other people have done this too, and so that's not true. The lowest mass ones, very low mass, do, but they're not a lot of mass function, and one of them is zero metallicity that have been calculated. A lot of these objects do not explode in 1D, but there are explosions in 1D that a number of groups are seeing. So we don't always need to get the turbulence. And these are just plots of the, let's see, these are entropy and pressure, and you can see sound waves. Those are sound waves. There's the shock, sound waves coming out. There's a lot of jostling going on. Mach numbers get up to half, things like that in the interior. This is just examples. And this Horowitz correction, which is the many-body correction that we're using, and it's not converged yet. We still don't know all the answers. When we conclude that, it explodes much earlier. And this is for the 9 solar mass that does not explode in 1D, but does easily explode in 2D at low energies. And so let me get to those. So you can see the types of waves that are coming out. The acoustic power is not very large. I had one time thought that could be large or could be important. And it's about the magnitude that we got originally about a number of years ago, 10 years ago, for acoustic power. But it's only 10% now because we got the neutrino mechanism to work. And here's a summary of some of the results in these low mass range, up to 10 solar masses, for example. In 1D, you get some models to explode, but many of them don't. This is just the average shock radius versus time. You put in 2D, most of those explode. Some of them have difficulty. In the 10 solar mass didn't explode. You'd think it would because it's a low mass. That's the lore, but that doesn't seem to be true. It explodes only when we include the many-body correction. That's when we don't, and that's when we do. And these are similar curves, but you can see the basic idea. And these are the explosion energies for these objects. For the lowest mass, we cannot get energies above about a quarter of a beta. Again, a beta is 10 to the 51 ergs. Standard being 1 beta. 87A being 1 to 1.5 beta. We do infer energies for explosions that are down to a tenth. So it may well be that nature is saying there is this range. But we haven't really determined that definitively, and we don't have the mapping between initial mass and energies really down. Although people are working on it, there's a lot of work to do. Let's see. Explosion energies. You can look at this in some detail, but the point is that the energies saturate really fast for the low mass end. It's over pretty quickly, and we're pretty confident, given the physics, that that's what happens. Oops. Let's see. And here's the masses. So here, for example, is the protoneutron star mass left behind. And you notice this is the baryonic mass. And you notice this curve here, we can leave behind what is gravitationally about 1.17 solar masses. And there is an observed neutron star at that mass. So we're getting the low end. I think we can easily get the high end. And again, these plots are just for the low progenitor mass range. We have other plots that I'm not going to show right now for this talk. There's also another thing that's curious, and this is just a mention in passing. You leave behind a protoneutron star. It's convective in the interior. The old Wilson model from many years ago, 3 decades plus, had convection in the interior, heating up the neutrino spheres and boosting the neutrino luminosities and getting an explosion. That was the delayed explosion mechanism. It was done in 1D. He needed convection to do it, but it was convection deep inside. We subsequently showed that the physics he was using, it was doubly diffusive instabilities, like salt finger instabilities, was wrong. Didn't work. This was also shown by Bruin and Deneva. And we've done it numerically as well, because we can do salt finger instabilities numerically, and they're not there. But what is there is regular mean molecular weight grade, mu grade instability. It just happens to be the electron fraction instability. And so you can have a molecular weight, mean molecular weight gradient equivalent, and there's convection in the interior. And it turns out that is actually important at later times for some of these models, which is really curious. And for the low mass end, we're getting a boost in the luminosity, which is more than 50%, which is much larger than I would have expected. And this is something new to emerge that might actually survive. And that's associated with the protoneutron star radius evolution. This is what happens in 1D, and this is what happens in 2D. And it's only because, the difference is only because there's the convection in the interior, which is changing the profiles. It's also associated with the boost in luminosity at later times for these models. So I want to quickly go through detections, and then I want to end. Neutrinos, of course, are the central diagnostic signature of the mechanism. And we've seen neutrinos from 87A. There were 11 from Kamioka 2, and there were 8 from IMB, and there weren't any credibly from other sources or other detectors. And this is just an example of that neutrino burst. It's amazing. But this was in the Large Magellanic Cloud for a detector that was only 2 kilotons. We now have detectors that are 40 kilotons with 22 kiloton fiducial volumes, and maybe even larger in the future. And we may get, if we're lucky, a galactic supernova, which would be 5 times closer, 25 times in the square, inverse square law. And so we expect to get interesting signals. This is an example. This is with Shaquan Cedro. We just take our models in the neutrino emissions and we convolve them through the detector sensitivity, ignoring oscillations, which is going to be a big thing. But I just want to show some of the basics. This is just what happens, the event rate, number of events per second in super Kamiokanda for an event at 10 kiloparsecs. And if we do the calculation in 1D, that's those thin lines here. No, it's thick lines here. So there's that red curve for one of the models. But if you do it in 2D, it explodes. You stop accretion and the luminosities go down. And there's more than a factor of 2 here. There's a factor of 2 there. There's a direct signature in the neutrinos of the explosion itself when it happens in real time. We'd love to see this. And this is just for a whole series of models. You do it in Super K. This is a subdominant channel, but this is the major channel for the interactions. And notice the interaction rates. This is 6,000, 10,000 events per second. Over a period of a second, you're going to get 6,000 events when you integrate under these curves generally. But a whole range. And notice something. You do it for one progenitor, these numbers are 4,000. You do it for another progenitor, that's 10,000. That's a huge progenitor dependence. You see with and without explosion, there's a factor of 2 between the explosion and no explosion. No explosion meaning doing it in 1D. So there are diagnostics in the neutrinos. It's the internal dynamics reflected in the neutrino signals themselves. And you can go through a lot of this stuff. I'm not going to. There's one thing that has a bearing on the gravitational waves in particular, which is when you have collapse and bounce, the first thing that happens in the neutrino sector is the breakout burst. There are breakout bursts in the optical, the ultraviolet, and the soft X-ray for classical supernovae, type 2 plateaus, blue supergiants. We saw indirectly, we didn't see it directly, that from 87A. When the shock hits the surface, the radiation floods out. Same thing happens in an atomic bomb in the atmosphere. You get the double hump structure that satellites are supposed to see, et cetera, that they might have seen in the southern oceans off South Africa. That's a different issue. But you get these breakout bursts. You get the same thing in neutrinos. And so you get this big burst of neutrinos. This is the same as the luminosity of the entire universe. I used to say this with pride until September anyway, because the gravitational wave emission is a few orders of magnitude larger in power. It's amazing, absolutely amazing. So that wins, of course. But the neutrinos are a good second or third. The point is that they announce the explosion in their timestamp. That's when things start. If you have a timestamp in your gravitational wave detection, in your gravitational wave retrieval attempts, then you can retrieve things a little bit more easily instead of going over many hours or many days. And so what you'd want to see is the neutrino burst. And you know where to look for the gravitational waves, because we assume that there is no dispersion in the speed of the gravitational waves. And for the neutrinos, there's very little dispersion, particularly for a galactic supernova. Okay, so that's a timestamp. And we can use that. And we can see how well we can actually measure these things, the breakouts, and this is as a function of distance. We include no oscillations in this, but you can see the red curve is at large distances. This is a detection rate in 10 to the 5 per second, so it's not that bad. But it's only over a few milliseconds for the burst. The rest of the neutrino emissions last for many, many seconds. We already have evidence for that, and that's what we predict as well. But if it's close, like 4 kiloparsecs, you get these whopping signals. And you can measure statistically. You put in some noise model, etc. You can measure how well you can measure the peak of the luminosity, the time that you reach maximum, how well, etc. And so you can get a delta T accuracy for when it started. And the numbers, if for galactic supernova, are generally on the order of a millisecond. These are other parameters of the breakout burst. How well can you measure these things when you know that this is a statistical thing, given the event rates? Okay, and then we could do this ad nauseum, and we have. For Ice Cube, which has a huge mass in the southern hemisphere, in Antarctica, you're going to get a huge number of events, but you won't be able to tag any individual events because it's going to just look like background. But the background level in Ice Cube, which has no sensitivity at these energies directly, will rise in unison and just go like this, back, up, and down, following the light curve. And you'll get a huge number of events. And so the accuracy with which you can measure these particular parameters of the breakout are much narrower. And if we have this whole flotilla of neutrino detectors, we'll be able to really pin down some of these characteristics. That would be amazing. We'd be seeing in real time what's happening in the supernova. And we've predicted so many things. If you don't see the breakout, if you don't see a lot of these details, we're wrong. Unfortunately, the breakout depends on the neutrino mass hierarchy when you put in the oscillations. And for the normal hierarchy, it's not there because it oscillates out. So I'm hoping for the inverted hierarchy.
What neutrino energy are talking about the ice cube? Is also an EV?
Yeah, this is tens of MeV. Yeah. You can't tag that. You can't get the energies, but you can get the background increase. You can get the energies for the highest energies if you can do multiple. If you get really high signal rate, because you're going to get some overlap, and they can sort of identify those. They think, but it's not going to be useful. They'll just try. Okay. There are lots of. I want to end with the gravitational waves.
You can smell the pizza, just so you know.
I can smell the pizza. Yeah. Okay. So I'm going to go quickly through this. This is to give credit where credit is due. That was quick. So what are the signatures? What is happening? I've described in broad outline the dynamics. But what we have in the gravitational wave signature is if it's rotating, you get a rotational bounce spike. With modest rotation, that spike is large. With rapid rotation, it's small. With no rotation, it's small. There's a sweet spot. You'll be able to see signatures of differential rotation. Remember I talked about perturbations. If you have significant perturbations, you have, early on, you start getting the turbulence, and that has a time-changing quadrupole moment. And then the turbulence grows and grows and grows. You get Mach numbers that start out at 0.1, 0.05, this sorts of things. You get up to 0.5 and higher. And that has a vigorous gravitational wave signature. And that would be in quote-unquote spherical symmetry, without rotation. So you have these various convections you might have a quiescent phase between the bounce, depending on the degree of perturbations and how much turbulence, and the full turbulence phase. So there may be an interesting ramp up. There's that inner convection as well. That inner convection that's where a lot of mass is, and so that inner convection is going to give you a big time-changing quadrupole moment. That transition to explosion is also going to be diagnostic. You're going to be able to see when the accretion stops, because the accretion is actually putting plumes, making plumes hit the surface. The surface is where the mass is, and so you start oscillating the inner core. That's where the gravitational waves are. If you stop that excitation, then that component goes away. You also get what's called Christodoulou memory. And I'll just show quickly because I have to end soon. There are lots of techniques for trying to analyze this. None of the techniques is adequate for these non-templatable things. So we need really high signal to noise to actually template it, to break it down. So that's one of the major issues. And that's some numbers. One of the curious things is that you get gravitational waves off the neutrino emission, because the neutrinos are being emitted anisotropically. And that gives you a time-changing quadrupole moment. The problem is that happens on long time scales, so it's at really low frequencies outside the LIGO band. In fact, it's between LISA and LIGO. So it's in the not-so-sweet spot. But we predicted this about 20 years ago, and there was a nice paper by Ruben Epstein in the late 70s that sort of said something like this. And the magnitude of the effect on the strain, D times H, is the same as for all these other things. It's just as the wrong frequency range. Okay. The magnitudes of the signals are something like this. And this is just the term, the quantities of art. This is ostensible advanced LIGO. I'm not on the LIGO team, so I can't put all the noise on there because I'm not allowed. They'll do something to me. Although I can use Inkscape and do a few things. I'm sorry. This is an example of this is a whole range of signals. That's one particular spectrum. You can see that things sort of peak around 500 hertz, 600 hertz. You get a whole range of frequencies, and that power is above advanced LIGO for 10 kiloparsec signal. We may need a fair amount of signal and noise, though, in order to see these things, so don't be too impressed. We might need signals and noise of on the order of 50. That depends. This is because these are bursty. Okay. As I said, if it's rotating really slowly, that rotational component is weak. This is beta, which is T over W, at bounce, which is large, but it starts out small. And so you get low rotation, modest rotation, high rotation. So there's a sweet spot, because if it's rotating fast, it will bounce centrifugally at low densities, and you don't get as much of a time-changing quadrupole moment. If it's not rotating at all, you don't get much of a time-changing quadrupole moment unless you break the symmetry by the turbulence, which you will. And so there's a sweet spot to the rotational effects. Okay. All right, hold on. I pressed the button too many times. And so there we go. And so this is the hydro on the left, and this is the corresponding signal on the right. You can see in this particular model, you can see the turbulence effects. Just watch what's happening. It's starting to jostle and slosh. And then when it explodes, the frequencies, I'm not showing the frequency, time frequency analysis, but that actually changes. But you can see what happens. You get memory. This goes off-center, and it stays off-center. This is a signature, again, of Christodoulou memory. It has to do with the persistent anisotropy of the result. It doesn't bounce out by going back and forth, back and forth. It explodes in one direction. So if you get a kick, if you have asymmetrical emission, if you have asymmetrical neutrino emission, that's going to imprint itself on a shift in the metric. That's called, but unfortunately it's at low frequency. But it's an interesting physical effect I always like to mention. This is other people's work, a nice work done by Yakunin et al. And this just shows the time frequency analysis versus time. This is 400 milliseconds, 600 milliseconds, and this is the type of frequency distribution with the peaks shown in that red curve. And that's a prediction for these types of models. This is the type of signal you get in H. These are the magnitudes you get. Now there was, and this is the equation of state dependence. You change the equations of state in these calculations, things don't change qualitatively, but you notice they do change, and you couldn't template that in the way we can do the emerging black holes. So we have to be a little bit more artful, and we need a higher signal to noise. Okay. There was one exotic context, which was if that oscillation of the proto-neutron star were really, really vigorous, and you excited quadrupole oscillations. Most of those oscillations are dipolar, and they have some quadrupolar component, of course. But if you actually excite strong quadrupolar oscillations, which was a factor in this acoustic mechanism I no longer believe is central, but is a small fraction of things, you get these huge signals. Huge signals in the detectors, and this is also an interesting characteristic. If this happens, it will completely swamp the gravitational waves. And you get an almost pure tone with a certain width in the detectors at a particular frequency, which is directly connected to the mean density of the proto-neutron star. This may not happen, but this is one unlikely but interesting possibility. And so this is just my summary. I've already done so. Thank you very much for your patience.
Well, we can get the lights, but everyone, I think Adam couldn't have fit more in his discussion. He's here for the remainder of today and tomorrow morning, so we can sign up and contact him directly or use the wiki page. I'm going to cut questions off so we can get pizza. If you want to approach him afterwards or meet with him afterwards, please. But I want to respect the people coming in afterwards. So again, let's thank him for an excellent talk.